O'Reilly!
It's Superstart Battery Month at O'Reilly Auto Parts. Get up to a $25 gift card after rebate with the purchase of select Superstart batteries. Our professional parts people will test your old battery for free and recommend the right battery for your vehicle. For power, performance, and reliability, choose Superstart batteries only at O'Reilly Auto Parts.
O'Reilly Auto Parts.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime Series 26, Episode 13, for broadcast on the 30th of January 2023. Coming up on SpaceTime, are Rubble pile asteroids older than we thought? Has the Earth's core stopped spinning? And another asteroid near miss of planet Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that so-called rubble pile asteroids can be almost as old as the solar system itself. A detailed examination of samples from a half-kilometre wide asteroid named Itokawa, which was around 2 million kilometres away, suggests that the cataclysmic impact which destroyed its monolithic parent body, leading to Itokawa's eventual formation, must have happened at least 4.2 billion years ago. The samples were part of a collection of dust and grain particles scooped up from the asteroid surface by the Japanese Aerospace Exploration Agency's Hayabusa-1 mission, which launched in 2003. Hayabusa-1 rendezvoused with Itokawa in mid-September 2005, studying the potato-shaped asteroid's surface structure, its spin, its topography, its color, its composition, its density, and its history. The spacecraft also carried a mini lander called Minerva, however that failed to reach the surface. Then in November 2005, 510-kilogram spacecraft landed on the surface of the asteroid and collected some tiny grains of asteroidal material for sample return to Earth. Hayabusa-1 returned to Earth in June 2010, parachuting its sample collection pod down into the Woomera rocket range in outback South Australia, where it was collected by a team of JAXA and Australian scientists. The study's lead author for this project, Professor Fred Jordan from Curtin University, says unlike monolithic asteroids, Itokawa is not a single lump of rock, but belongs to the Rubble pile family of asteroids, which means it's made up entirely of gravitationally bound loose boulders and rocks and dust, with almost half of it being empty voids. The findings were reported in the Journal of the Proceedings of the National Academy of Sciences, based on detailed studies of just 3 of the tiny dust grain particles collected from Itokawa's surface. The authors were interested in examining the durability and age of asteroids made of rocky rubble and dust, and they used 2 complementary techniques to analyze their samples. The first was electron backscatter diffraction, which was used to measure whether the rock itself had been shocked by meteor impact. The second method, argon-argon dating, was used to actually physically date the asteroid samples, and that gave them the astonishing date of 4.2 billion years. The survival time of monolithic asteroids the same size as Itokawa in the main asteroid belt has been predicted to only be several 100,000 years or so. So the astonishing long survival time of an asteroid the size of Itokawa is being attributed to the shock-absorbent nature of rubble pile asteroids. Jordan says, think of Itokawa like a giant space cushion. The durability of rubble pile asteroids was previously unknown, thereby jeopardizing the ability to design defense strategies in case one of them was found hurtling towards the Earth. The findings suggest that rubble pile asteroids will be difficult to destroy because they're resistant to collision. Jordan says they've found that these rubble pile asteroids can survive in the solar system for almost its entire history and must therefore be far more abundant in the main asteroid belt between Mars and Jupiter than previously thought. That means there's more chance that if a big asteroid is hurtling towards the Earth, it'll probably be a rubble pile. So, with these asteroids being resistant to being shocked or fragmented easily, Jordan says the good news is that rather than a kinetic push, using a shock wave from a nearby nuclear blast could well do the job of pushing the asteroid off course before it impacts the planet.
In 2010, JAXA brought back samples from Itokawa, and the mission partially failed actually. So they were thinking about getting few milligrams to grams, but actually they just had 1,000 particles. So they were really, really priceless. And a few questions arise around those particles, and a big one was, when did Itokawa form? And by form, I mean every solid chunk of asteroid, monolith asteroid as we call them, they pretty much form at 4.6 billion. But Itokawa is not a monolith asteroid, it's a rubble pile. So in a sense, it's made of fragments, boulder, rocks, pebble, and dust, due to the complete shattering of its parent body during a catastrophic impact. And the entire JAXA community and everybody working around the sample, they were really curious when that it happened. So what we did, we asked JAXA a few particles. They were generous because the technique we use are destructive. So once we're done with our sample, they're gone forever. But they were okay with that because the question we address is pretty interesting. And we look at them using the EBSD technique. So it's an electron backscatter diffraction. And what it does, it looks at the level of shock deformation in the grain in the crystal structure. And the other technique we used was argon-argon dating. So it's based on the decay of potassium in argon. So potassium is pretty much everywhere. You contain potassium, I contain potassium, and pretty much every rock contains potassium. And so it decays into this argon, and it's a geological clock. When you have an element which is radioactive, the potassium, it's going to decay in argon. And this atom, the atom of argon, is trapped in the structure of the crystal. It doesn't belong here, but it's completely trapped like it's in a jail. If you apply more heat, what happens to every atom in the crystal is they move faster, because this is what heat is all about, atom moving faster. And if you reach a sort of escape velocity, if you want, it moves so fast that it's going to move randomly through the structure, through Brownian motion. And when it reaches the surface, it just go away. And you keep losing argon from your crystal. And in the case of the one we dated, it's mostly plagioclase. And plagioclase close at 300 degrees. So if you apply a temperature of more than 300 degrees for a few hours to a few days or months or whatever, then all the argon is going to be purged until the system cool down back below 300 degrees and the argon starts accumulating again. And that's what happened at 4.2 billion. The system gets completely reset and get trapped in the rubble pile structure and start to accumulate again. What happened is, like at the beginning of the solar system, this clock starts in the parent asteroid. And if nothing would have happened, we would have get a chunk of rock dated 4.6 or 4.56 billion, like we did many chondrite. But in this case, the age that we got on Itokawa was different, 4.2 billion years old. This was surprising, and not in the sense it was too young, but rather it was really, really old. Because remember that Itokawa is fragmented by the impact that fragmented the monolith asteroid. So when it gets fragmented, the clock resets. So we can essentially date the fragmentation. But why I say that it's older than expected? Because a lot of people have run model simulation, and it's estimated that asteroids between 500 meters to a kilometer, 2 kilometers in size, they're supposed to survive few hundred million years in the asteroid belt and get destroyed by constant bombardment. But here the age is not few hundred million, it's 10 times older, 4.2 billion. So that was much older than what people anticipated.
These are rubble piles. They're dust and grains and rocks of various sizes. You'd think that over millions and billions of years, just the solar wind alone would be eroding the surfaces of these things away. But they've held up. 4.2 billion years is a long time.
Yeah, because solar wind is gonna do its work, especially on the dust. The thermal expansion contraction is gonna do its work, so it's gonna fracture the rock as well. You know, when it's lighted by the sun or when it's in the shade, different temperature. But the most destructive force around is by other asteroid impacts, so small one. So in the asteroid belt, the small one, they keep constantly impacting the big one, and all those simulations that tells us, look, it's getting smaller and smaller, and over a few hundred million of years, it just completely disappears. But that was paradoxal that an asteroid like Itokawa, so when people think about rubble piles, people think that those asteroids are completely fragile. You just shoot something into it, it just scatters apart because it's largely bound by gravity. But that's not the case. That's exactly the opposite that happens. If you shoot an asteroid in it, a small one, well, if it's too big, of course, everything is going to be destroyed. But if it's small, what's going to happen is going to just smack into it, and all the energy is going to be absorbed.
And Itokawa is what, about 50% empty?
Yes, the exact number is 40%, so you weren't not far, but this is exactly what it is. It's void space. And that's why I like to call Itokawa a space cushion, because it's mostly void and it absorbs energy. The analogy I love giving people is they go in their backyard and they put a rock and they use your sledgehammer to fracture it. Huge impact energy, maybe it's going to fracture in 3-4 pieces, big pieces, right? But if you do the same with a pile of small pebble or sand, just the hammer is going to do poof in the sand and nothing's going to happen. The pile of sand is going to look exactly the same. Why is that? Because the energy is completely absorbed by the void space. And that's exactly what happened with Itokawa.
Now, looking at a rubble pile asteroid like this, that's got to have implications for the future of things like planetary defense, especially when you consider that we saw pretty much the same sort of thing with the DART mission recently.
Absolutely. And I'm a big fan of the DART mission. That was a fantastic, resounding success. I mean, it works even better than intended. So what they did is they used a small space probe the size of a refrigerator, and they impacted in a moon Didymos. So the moon is called Dimorphos. Both asteroids are rubble piles. They are fairly small, 200 meters wide. And they managed to deflect the Dimorphos, change its orbit by half an hour or something like that. And that was more than what people thought it would be. And sometimes people tell me, oh, so you reached the opposite conclusion with your studies that like asteroids are resistant. No, we reach exactly the same conclusion. This is fantastic. But the fact that they are resistant can help us in this following case scenario. So for moving an asteroid with kinetic impact like they did for Dimorphos, you need to at sea know the asteroid is coming, send a probe a few years to a few months if you're lucky in advance, and that's a lot of preparation time. But what if we detect the asteroid a month before it hits, right? It's just too close. The kinetic impactor is not going to work. So what we're saying is like those asteroids, they survive so long in the asteroid belt. What it means is like they can take a serious beating by other asteroids bombarding them. So what we propose is to use a more drastic approach, if needed, like the explosion of a nuclear device. Now, immediately people think, oh, Armageddon, you want to destroy asteroids. This is not the case at all. What we're saying is like, we should put a nuclear device on the side of the asteroid, and the shock wave is going to push it out of the way, not destroy it. And that's what we want. We want to keep it intact, but we want to push it. And people are like, whoa, yeah, okay, it can survive bombardment, but the nuclear device is way more powerful. No, it's not. If you take the case of Chelyabinsk, that was the energy of 20 to 30 Hiroshima bombs, right? So that's much more energetic. So those impacts are much more energetic than the kind of device we might need to use in this case. And overall, that's not a doomsday scenario. It's a good news. We can use this quick fix technique to deflect an asteroid out of the way. But it's better if we know years in advance so we can use more controlled experiments.
Now, there are two other asteroid missions you're currently involved in. One of them, OSIRIS-REx, is due to return to Earth this year.
Yeah, absolutely. So it comes back from asteroid Bennu, which is fairly exciting for me because it's also a rubble pile asteroid. And it's a different type than Itokawa. Itokawa is more chondritic. This one is carbonaceous chondrite. So we're going to try to answer a different type of question. But with my technique, I'm especially interested in when did this rubble pile form as well. And we get the sample coming back to us the 23rd of September this year. And they're going to be moving around labs fairly soon after that. So yeah, pretty excited by this one. The second mission that I'm involved with is the MMX mission. So it's more far in the future, but this one is very interesting nevertheless. The JAXA, Japanese Space Agency, is going to send a probe to one of the moons from Mars, Phobos, and they're going to collect sample there as well and return back to the Earth. The big question that they want to answer is it a capture asteroid? Because it's so small, it can't be like a moon like ours. Or is it something that comes from the surface following an impact? So a bunch of debris reagglomerated together around now.
That's Professor Fred Jordan, the director of the West Australian Argon Isotope Facility at the School of Earth and Planetary Sciences at Curtin University. This is SpaceTime. Still to come. Has the Earth's core stopped spinning? And another asteroid near miss of planet Earth. All that and more still to come on SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
A new study claims the rotation of Earth's solid inner core may have recently paused and could even be reversing. The suggestion, reported in the journal Nature Geoscience, is based on an analysis of seismic waves from earthquakes which have passed through the Earth's inner core since the 1960s. Scientists first confirmed the existence of Earth's core in 1936 after studying how seismic waves from earthquakes travel through the planet. Changes in the speed of these seismic waves revealed that the planet's core, which is about 7,000 kilometers wide, consists of a solid inner core, composed mostly of iron and nickel, surrounded by a molten metallic outer core, composed mostly of liquid iron and other elements. As molten iron from the outer core crystallizes onto the surface of the inner core, it changes the density of the outer core liquid, in the process driving churning motions that help maintain Earth's magnetic field. The liquid outer core also acts to decouple the 2,400 kilometer wide inner core from the rest of the planet, allowing the inner core to rotate at its own pace. The spin of the inner core is thought to be driven by the magnetic field generated in the outer core and balanced by the gravitational effects of the surrounding mantle. Scientists have found that since the 1960s, the time it takes for seismic waves to reach a given seismic station from earthquakes originating the same place on the other side of the planet has changed, suggesting that the inner core is rotating faster than the planet's mantle. That's the layer above the outer core. Follow-up studies have now determined the rate of this superrotation, as it's called, suggests that the inner core rotates faster than the mantle by about 1/10 of a degree per year. They've also identified a reversal in the inner core rotation as part of a 7-decade oscillation, with a previous turning point occurring in the early 1970s. However, other studies have suggested that this superrotation only really happens in mostly distinct periods, such as in the early 2000s, rather than as a continuous steady phenomenon. And there are other scientists who argue that the superrotation doesn't exist at all, and that the differences in earthquake travel times are actually being caused by physical changes on the surface of the inner core itself. And then to further complicate things, you may recall that last year we reported on a study using data from seismic waves generated by American nuclear tests in 1969 and 1971. These suggested that between those years, the Earth's inner core rotated more slowly than the mantle, and that it only began to increase its spin rate above that of the mantle after 1971. But now the authors of this new study say that the inner core has stopped spinning relative to the mantle. The claim, that's based on earthquakes between 1995 and 2021, suggests that the inner core superrotation stopped around 2009. And they say they've observed the same effect at different points around the globe, thereby confirming that it is a true planet-wide phenomenon related to the core's rotation, and not just because of a local change on the inner core surface. They say that since around 2009, paths that previously showed significant temporal variation have exhibited little change, suggesting that the inner core's rotation might be in the process of shifting back towards subrotation, or it may have paused altogether. If so, something's probably happening to the magnetic and gravitational forces that drive the inner core's rotation. And these changes might link the inner core to wider geophysical phenomena, such as changes in the length of the day on Earth due to shifts in planetary rotational speeds. Now, if it's all correct, the findings could aid science's understanding of how processes deep in the Earth affect the planet as a whole. After all, knowing how the inner core rotates would help illuminate exactly how these different layers all interact. However, the speed of this rotation, and whether it varies at all, is still hotly debated. This is SpaceTime. Still to come, an asteroid the size of a huge truck swoops past the Earth, and later in the science report, United States approval given for a new generation of small modular nuclear reactors to combat climate change. All that and more still to come on SpaceTime. An asteroid the size of a big truck has just swooped past the Earth, making one of the closest approaches by a near-Earth object ever recorded. Asteroid 2023 BU passed just 3,600 kilometers above the southern tip of South America. That's 10 times closer than the orbits of geostationary satellites. The 8.5-meter wide space rock was discovered just a week before its close encounter with planet Earth by citizen scientist astronomer Gennady Borisev, the discoverer of the interstellar comet 2I Borisev, from his observatory in Crimea. Additional observations were then reported to the Minor Planet Center. That's the internationally recognized clearinghouse for the position measurements of small celestial bodies. And the data was then automatically posted to the Near-Earth Objects Confirmation page. And after sufficient observations were collected, the Minor Planet Center announced the discovery. Within 3 days of notification, a number of observatories around the world had begun making dozens of observations, helping astronomers better refine 2023 BU's orbit. With that information, NASA's Scout Impact Hazard Assessment System at CNEOS, that's the Center for Near-Earth Object Studies at NASA's Jet Propulsion Laboratory in Pasadena, California, analyzed the data and was able to confirm that it should be a near miss rather than an impact. But it was also going to be an extremely close shave. NASA's David Finocha, who developed Scout, says it was one of the closest approaches by a known near-Earth object ever recorded. CNEOS calculates every known near-Earth asteroid orbit in order to provide assessments of potential impact hazards in support of NASA's Planetary Defense Coordination Office. While any asteroid in Earth's proximity will experience a change in its trajectory due to Earth's gravity, 2023 BU came so close that its path around the Sun is expected to be significantly altered. Before encountering the Earth, the asteroid's orbit around the Sun was roughly circular. In fact, it was approximating Earth's orbit, taking roughly 359 Earth days to complete one orbit around the Sun. But following its encounter with Earth, the asteroid's orbit has become far more elongated, moving it out to about halfway between Earth and Mars at the furthest point of its orbit around the Sun. That means 2023 BU will now complete one orbit every 425 Earth days, giving us something to look forward to in a year and a couple of months. This is SpaceTime.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
And time now to take a brief look at some of the other stories making news in science this week with a science report. America's Nuclear Regulatory Commission has for the first time given its stamp of approval to a new next-generation small modular nuclear reactor design. Certification of the new-scale design allows utilities to choose the advanced reactor when applying for a license to build and operate a new nuclear power plant. The argument in support of these small modular reactors is that they don't emit greenhouse gas emissions, and that they can provide much-needed backup baseload power in support of solar and wind energy, which tends to fail when the sun doesn't shine and the wind doesn't blow. And apparently batteries aren't the answer, because it would take 30 years to mine enough lithium to build enough batteries. And that entire process causes its own environmental problems. And because they're small and modular, these next-generation nuclear reactors can be completely self-contained and built on the grounds of existing coal-fired power stations, thereby saving trillions of dollars in poles and wires infrastructure costs. And because they're factory assembled, they're both cheaper and easier to build than traditional nuclear power plants. The certified design is about a third the size of a traditional reactor, and it's based on a concept developed by Oregon State University back in the year 2000. Similar reactors have been used on nuclear submarines for decades. The current design is approved to generate up to 50 megawatts of electricity, although N-scale is applied to increase this up to 77 megawatts. The current proposal would see a demonstration plant built in Idaho with 6 modules collectively producing 462 megawatts. The power station should be complete and operational by 2029. A 1,550 square kilometre iceberg, almost the size of Greater London, has broken off the Brunt ice shelf in Antarctica. British Antarctic Survey scientists who have been watching the iceberg say they've seen cracks develop over the last few years, and say one crack finally extended through the whole shelf on January the 22nd, causing the iceberg to physically break free. The researchers say it's quite natural for icebergs of this size to break off the Brunt ice shelf, and it's not related to climate change. The Bulletin of Atomic Scientists has reset the famous doomsday clock to just 90 seconds to midnight. That's the closest the clock's ever been to the end of the world since it was first established in 1947. Scientists say the change was due to the unprecedented danger being posed by Russian President Vladimir Putin's repeated threats to use tactical nuclear weapons as part of its ongoing invasion of Ukraine. The hands of the clock are set each year by the Bulletin's Science and Security Board, which includes 10 Nobel laureates. When the hands of the doomsday clock were last moved, they were set at 100 seconds to midnight. That was in 2020. Scientists at the time said it was driven by the risk of civil collapse in the event of nuclear weapons use and the climate change crisis, compounded by the threat multiplier of cyber-enabled information warfare, resulting in the world being at a profoundly unstable point in history. The closest the clock came during the height of the Cold War was 2 minutes to midnight. That was in 1953, following the first hydrogen bomb detonation. At the time of the Cuban Missile Crisis, the hands were 7 minutes to midnight. But the Bulletin's board decided not to move them despite the crisis. That's because by the time it came to make that decision, the near catastrophe appeared to have given both Washington and Moscow fresh impetus to work towards risk reduction and arms control. The clock reached 9 minutes to midnight in 1998 following tit-for-tat nuclear tests by India and Pakistan, and 5 minutes to midnight in 2006, following North Korea's first nuclear test. The World Health Organization is continuing on its path away from science-based medicine and down the rickety track of dangerous alternative so-called traditional treatments. The WHO has lost a lot of credibility and suffered strong criticism from scientists recently after underestimating the deadly lethality and global spread of COVID-19 at the behest of China. It was also slammed by real medical doctors for its support of traditional Chinese medicines, including acupuncture and the use of animal body parts from rare and endangered species, which have no proven scientific benefit other than as a placebo. Now the World Health Organization is showing its support for traditional Indian Ayurvedic treatments. Tim Mendham from Australian Skeptics warns that, like their Chinese counterparts, these traditional Indian remedies are pure pseudoscience, which often only work as a placebo and can be extremely dangerous.
Yes, there's been a recent occurrence of the Indian government pushing Ayurveda, which is their sort of ancient version of herbal treatments for basically every disease you can think of. Now, this has been around for a while. There's a lot of treatment for it. There's a lot of support from the Indian government. They've actually set up a department to look after such medicine and such treatment. The most interesting thing is that recently they opened up a $250 million investment in a centre for investigating this traditional medicine, but it's called the WHO, Global Centre for Traditional Medicine. In other words, the World Health Organization is also supporting it. And when they opened it, the Indian Prime Minister Narendra Modi sat next to the Director General of WHO as they celebrated the growing global impact of traditional Indian medicine. The trouble is, there is absolutely no proof that Ayurveda works any more than any herbal treatment, and many herbal treatments don't work that well. Even though people keep claiming, we get a lot of our medicines out of herbs, so the original treatment is sort of proving valid. Well, actually, the treatment is not valid. The source might have some validity, the particular herb, and certainly there are some treatments like artemisinin for treating malaria, but that's only because people have actually refined it and found out that there is something there, whereas the original treatment is largely a waste of time because you're in such small doses for things that you need huge doses, which you only get when you refine it. The important thing is that this event from promoting Ayurveda Day with the Minister for Ayush, which covers everything including homeopathy, which we know doesn't work, and the sad thing is that it's getting the endorsement of the WHO. The WHO has been interesting lately because it has been endorsing traditional Chinese medicine as well. And there's been suggesting that some of the people in the WHO have a proclivity towards sort of some of this alternative stuff.
Oh, you think?
I do think, and that's a real concern, actually. That
I think anything Tedros is involved in is a real concern. His own background is somewhat dubious.
I don't know him, actually, I must admit.
He only got the gig because of Chinese support. China had enough votes in the WHO to get him the top job, and since then he's basically kowtowed to everything they've wanted, as long as he gets paid for it. And he's made a lot of money out of the WHO.
So he's basically in the pay of big business, actually, in this particular case. Big alt business. So, the Chinese are now India. And the previous WHO head was a Chinese woman who was also, she started this thing, really, as far as I know, of pushing traditional Chinese medicine, which there's no basis for either. And the WHO does do good works in terms of vaccination and things, but supporting
the rank and file of the WHO are fine. It's the corrupt officials at the top of the organisation that really need to be removed. And until government, because that's all funded by individual governments, and until governments decide to do something about it, the corruption in the WHO will continue. Yeah,
very sad. Very sad. I mean, it must be galling to the people who are doing real medicine. The WHO suddenly find all this effort. $250 million investment in this centre, that's US dollars, is a lot of money that the WHO could spend doing other things.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies. Or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.